So for problem number 45, I'll read it to you guys out loud first, and then we'll go from there. So problem number 45 is on angular acceleration, and it says a merry-go-round accelerating uniformly from rest achieves its operating speed of 2.5 RPMs in 5 revolutions. What is the magnitude of its angular acceleration? So let's unpack that so we get an idea of what we're talking about. I have a merry-go-round.
Looks like pizza.
Okay, and the merry-go-round spins around. Okay, and according to this, it says that it makes 2.5 revolutions, or it operates up to a speed of 2.5 RPMs. Okay, so now what that means is that its angular velocity is 2.5 revolutions per 1 minute. Right, that's what RPMs are. Revolutions per 1 minute. RPM, revolutions per minute. Now, it says it does that in 5 rotations. So after so this is technically like its final angular velocity. So let me read this again out loud. It says a merry-go-round accelerating uniformly from rest achieves its operating speed of 2.5 RPMs and 5 revolutions. What is the magnitude of its angular acceleration? So what was its initial angular velocity? If it started from rest, what was its initial angular velocity? 0. And what is it asking for? Well, it says that it accelerated uniformly. What does uniformly mean with regard, if it says it accelerated uniformly, what does that mean?
The same.
The same or constant. So it's a constant acceleration, okay? So if it's a constant acceleration, that means that we're looking for this, okay? Now we use alpha for angular acceleration. That's the Greek letter alpha. Let's do a quick review of that. Anybody remember what this Greek letter is?
It's the
Omega, right? It's lowercase omega. This one is alpha. Now this one is angular acceleration, and this one is what? Does anybody remember? Angular velocity. Now, or speed. Usually it's speed, because if I say velocity, but I don't want to ignore that. So it's either velocity or speed, but usually we say speed, because velocity is a vector, and if something's rotating, that means that the direction is constantly changing, and so on and so forth. All right. So we want to find out what alpha is. The only problem is that we need to do something else. So if we do our problem-solving process, our physics problem-solving process, first we read the problem, then we draw the picture. Well, I guess the first thing we would do is go to courtesy mode, right? Then after we're in courtesy mode, right? Well, I mean, the first thing we would do is like make sure our cell phones are not on our desk. Then the next thing would be make sure we're in courtesy mode. The third thing then, I guess, would be is to draw the picture, right? Read the problem, draw the picture. I lost track of first, second, and third, so we'll just go in order. Draw the picture, label what we know, label what we don't know, and then what's next after that?
Equation.
We got to find an equation. Now look, if you go in, everybody open up your textbooks to page 256 and 257. Okay, so look in your textbooks on. If you don't have your book with you for whatever reason, shame on you. But you can look on with a neighbor. Okay, and it's actually 256. But the formula that we need is 256. If you look on page 256, which formula can we use?
Angular.
Do we know the time? No? Now I know which one we should use. I'm going to write it down on the board. Okay? The one that we should use is omega squared, final omega, is equal to the initial omega, right? The final angular velocity is equal to the initial angular velocity plus 2 times the acceleration alpha and then delta omega. Do we know omega? Now remember, omega is an angle, right? Or not omega, do we know theta? I'm sorry, I apologize, too many Greek letters. Theta represents an angle in radians. Do we know how many radians the merry-go-round rotates?
Yes.
Okay, 5. Let me ask you a question, you guys ready?
Yes.
Okay. I do 1 revolution or rotation. How many radians is that? 2 pi. I do that 5 times. Now what was my initial position? 0. Right? And then I moved 5 pi. So way down here, what I moved was 5 pi. So if I start to fill some stuff in, this has to be changed. But what was my initial angular momentum? 0. So this goes away, doesn't it? Okay. And we're solving for alpha. So let's do something a little different. Let's solve this algebraically. If this equals 0, that goes away. So then I have this is equal to 2 alpha omega. Right? So then if I divide this by 2, and I keep saying omega, but it's theta, right? You guys don't listen to me. Watch what I write on the board. Is that the same? Algebraically speaking?
Yes.
Yeah? I didn't feel like writing down the delta. I suppose if we wanted to be real formal, we could say delta theta. Doesn't matter. Only one other thing I have to do. Before I plug that in, this needs to be revolutions per what? Per second. So I need to convert that. How do I come up with that number? Well, how do we calculate angular velocity? We'll come back to that. What's the relationship between, well, what is, how do I I'm trying to figure out how to word this. We know that this, our final angular speed, I should say, 0.5 revolutions per minute, right? If we go back to the picture, well, what is the unit of measure of this? You guys remember that? Because we're going to use some dimensional analysis. How do we figure out what our angular speed is? Consider this relationship though. We know that omega is equal to this times time, or another way to write it is angular velocity is equal to the change in theta over time, right? Or the change in theta over time, right? If that was the average angular speed, isn't that how we would get that? You guys remember when we derived that in class? So for this section, if I'm only talking about units of measure, dimensional analysis, how do we measure theta? What is theta measuring? Angles, right? And how do we measure angles for this class? We could use degrees, but what do we really want to use? Radians. And what's our standard unit of measure for time? Seconds. So right now, I have 2.5 revolutions per 1 minute. And you guys were half right. We were going to need to convert that 1 minute into seconds. But what do I need to convert? I don't need to write out seconds. We'll just write out. So that's right, but I need to do one more conversion. Revolutions per what?
1 second.
So 1 revolution equals, I need radians. 2 pi. So 2 pi radians is equal to 1 revolution, right? So now this cancels with this cancels with this. So I'm going to take 2.5, whoops, gotta put my marker back. Let's clear this out. And let's do, let me clear all this out. 2.5 times 2 times pi. And then we're going to divide all of that by 60, right? And we get 0.26. 0.262 radians per second, right? So we did all that work to say that this was 0.262 radians per second. That was a lot of work, wasn't it? Does that make sense, though? Can't forget that. So are we done? No. We've got to plug that into this fancy formula we came up with. So basically, our angular acceleration is equal to 2.62 radians per second divided by 2 times 10 pi radians. Does that make sense? But this whole thing has to be squared. And so if you square the whole thing, you'll end up with, well, let's just see what we get. If I do 2, let's see what we get. Let's crank through the math. 0.262 squared. Then we're going to divide that by, what's that, 20 pi? So if I say divided by 20 times pi, I get 0.001. Something like that. Now I'd like to write that in scientific notation, so I have to move this 1.3 spaces, right? I go 3 spaces, so I'm going to say 1.1 times 10 to the negative 3. And then for my angular velocity, I'll have, there's a radian here that cancels with the 2 up here, so then I get radians per second squared, so it matches up. Was that the answer in the back of the book? Now, we did a little bit of work there, and as I look at you guys, you kind of got like this a deer lost in the headlights kind of look. So let's talk about what we did. I'm going to read this. We always want to do like a common sense check at the end, all right? So we'll read the question again and see if we're answering the question correctly. It says a merry-go-round accelerating uniformly from rest achieves its operating speed of 2.2 revolutions per minute in 5 revolutions. What is the magnitude of its angular acceleration? In other words, how many degrees per second does this thing keep moving? Okay? So if I were to draw a line right here, let's use blue. If I were to draw a line right here, what is the angle of this thing rotating constantly? How does it keep speeding up? Right? Because acceleration is change in velocity. Well, whatever that number is, whatever that value is, by the time it rotates or makes 5 revolutions, it should be operating at 2.5 revolutions per minute, 2 RPMs. Does that make sense? So then we had to go through and look at our circular, I call them uniform circular kinematics, because that looks just like our 2-dimensional kinematics, or actually linear. But anyways, which is the velocity, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position, but in this case it's change in theta, because that's how we're measuring the displacement. Well, we're lucky because it started from rest, so the initial angular velocity or speed is 0. So 0 squared is 0, so we get a simpler equation here. We're solving for alpha. Theta we have to kind of figure out, and then we want to convert this to the proper unit, dimensional analysis, right? So in order to get theta, we said, well, what's theta? Theta is a measure in radians. It's an angle. And we know that it's going to change 5 revolutions. For each revolution that we go around, it's equal to 2 pi. We're going to do that 5 times. So theta is actually 10 pi. So we plug that into our formula way down here as 10 pi. Lastly, we are given this in revolutions per minute. That's great, but we really need it in radians per second because that's the standard unit measure, right? So we go through all this math to make sure that it's in the proper units. And then we just plug it into this simplified equation and we get 1.1 times 10 to the negative 3 radians per second. So really, it's a very small amount.